Good morning, students. In a previous class, that is class 2 of the chapter solid state, I already completed giving a little idea about the three-dimensional closed packing, that is hexagonal closed packing and cubic closed packing. Next, the packing efficiency or packing fraction. What is a void or hole? Type of void, tetrahedral void, octahedral void. Then coordination number. Then radius ratio. And finally calculation of density for unit cell. Today, that is class 3 for the chapter solid state. I will try to complete the imperfection or defect in crystal. Generally, this defect or imperfection arises due to some disturbances, due to some deviation in normal arrangement, in ideal arrangement, and it is due to the heat absorbed by the crystal from the surrounding or by the addition of some impurity. When this disturbance or irregularities appear around a point, then it is known as point defect. Generally, point defects are classified into three types. That is, one is stoichiometric defect, one is non-stoichiometric defect, and one is impurity defect. Let I draw this one in the form of a flow chart for better understanding. Mark that. First one is defects, classified into three types. One is stoichiometric defect, one is non-stoichiometric defect, and third one is impurity defect. Impurity defect. Mark that. The point defect is classified into three types. One is known as stoichiometric defect, one is known as non-stoichiometric defect, and one is known as impurity defect. Come to the point one, that is stoichiometric defect. It is again of two types. That is, one is known as vacancy defect, and one is known as interstitial defect. Interstitial defect. These two defects are for the non-ionic solid. But if we discuss about the ionic solid, in case of ionic solid, this is of two types. One is Schottky defect. One is Schottky defect, and one is Frankel defect. In case of ionic solid, this stoichiometric defect is of two types. One is Schottky defect and one is Frankel defect. Next, come to the non-stoichiometric defect. It is of two types. That means one is known as metal excess defect. Metal excess defect, and one is known as metal deficiency defect. Metal deficiency defect. Mark that. This non-stoichiometric defect is of again two types. Arises, one is due to metal excess defect and is metal deficiency defect. This metal excess defect is again classified into two types. One is due to the presence of defect due to the presence of extra cation occupy in the interstitial site, occupy in the interstitial site, and another one is due to anionic vacancy, due to anionic vacancy. Mark that. This is the total flow chart. I repeat again. This point defect is of three types. One is stoichiometric defect, non-stoichiometric defect, and impurity defect. In case of non-ionic crystal, this stoichiometric defect is of two types. One is a vacancy defect, one is interstitial defect. And for the ionic solid, it is of two types. Very, very important one for council point of view. That is, what do you mean by Stokes defect? What do you mean by Frankel defect? Or the question is, give a distinction between Stokes defect and a Frankel defect. It is all about the stoichiometric defect. Next to non-stoichiometric defect, that is of two types. One is metal excess defect, one is metal deficiency defect. Again, metal excess defect arises due to 2 points. One is the presence of extra cation in the interstitial site, and one is due to anionic vacancy. And last one is impurity defect. Let us discuss one by one. That is, point one is stoichiometric defect. What do you mean by the term stoichiometric defect? This defect arises in case of ionic crystal. This defect arises in case of crystal when this defect does not change the formula for the ideal arrangement. I repeat again, this defect does not change the formula for the ideal arrangement, and this defect arises due to the missing of pair of cation in the interstitial site. Mark that. It is again of two types. One is known as vacancy defect, one is known as interstitial defect. Come to the point one, that is known as vacancy defect. In this defect, in case of crystal, in this defect, some of the lattice site are vacant. I repeat again, in case of vacancy defect, some of the lattice site are vacant. Then this type of defect is known as vacancy defect. While in case of interstitial defect, that means some of the lattice site are vacant, but that metal ion is present, but that constituent particle is present in the interstitial spaces. So this type of defect is known as interstitial defect. In case of a vacancy defect, as some of the lattice site are vacant, it decreases the density, while in this case interstitial defect, there is no decrease in density. Mark the graphical representation. Mark that. In this case, some spaces are there. Mark that. This is the space is there. Means vacant. Here is also space is there. Vacant space is there. It is a missing. As a result of which it decreases the density. As it deviates from the regular arrangement, it is known as vacancy defect. On the other hand, the interstitial defect, if we discuss about the interstitial defect, then a defect is there. That means it is some of the constituent particles are present in the interstitial space. So this type of defect is known as, that is, interstitial defect. And these two are, for the case of non-ionic solid, here there is no decrease in the density, while the previous case, in case of vacancy defect, there is a decrease in the density. Next, for the ionic solid, for the ionic crystal, Again, this stoichiometric defect is of two types. One is Schottky defect, one is Frankel defect. So before going to the Schottky defect and Frankel defect, I come to this point one, that is a vacancy defect. Why it is a vacancy? It is due to the heat absorbed by the crystal, from the surrounding. The most important thing is that this defect arises due to the heat absorbed by the crystal from the surrounding. Come to the point. In case of ionic crystal, it is of two types. One is known as Schottky defect, one is known as Frankel defect. Come to the point one, that is Schottky defect. This defect arises in case of ionic crystal, which is represented by A plus B minus. Mark that. In case of ionic crystal, which is represented by A plus B minus, A plus B minus, B minus A plus. That means what do you mean? Before going to the structure, let us discuss what is the Schottky defect. In case of ionic crystal, when a pair of cation and anion is missing. In case of ionic crystal, when a pair of cation and anion is missing, then this type of defect is known as Schottky defect. As there is a pair of cation and anion is missing, it maintains the electrical neutrality, and also there is a decrease in density. This type of defect is shown by highly ionic compound, which one possesses high coordination number, and there is a small difference in the size of the cation and anion. Mark that, the structure B minus, A plus, B minus, A plus, B minus, B minus, A plus, B minus, A plus. Mark that here. Here is the cation is missing. After B minus, A plus is there. Cation is missing, anion is missing. A pair of cation and anion is missing, as a result of which maintain the electrical neutrality. And as the cation anion is missing, it decreases the density. And the most important condition is that is this type of defect shown by ionic compound which possesses high coordination number, and there is a small difference between the size of cation and anion. Suitable example: sodium chloride, potassium chloride, potassium bromide, silver bromide. Mark some examples. Examples are sodium chloride, potassium chloride, potassium bromide, silver bromide. These are the ionic crystal, ionic solid having high coordination number, and there is small difference between the size of the cation and anion. Move to the next one, that is Frankel defect. It is also shown by the ionic solid, ionic crystal, where cation is missing from the lattice side, but it is occupied in the interstitial space. As a result of which, there is no change in density. And this type of defect is shown by ionic compound having low coordination number, and there is a great difference, large difference in the size of cation and anion. Mark that. A plus, B minus, A plus, B minus, B minus, A plus is missing, it is present here, B minus. These are the defect shown by, it is the defect shown by ionic solid, and it is known as Frankel defect. That is, cation is not present at the normal lattice side, but it occupies the interstitial space. And as there is no deviation, that means there is no decrease in density, and this type of defect is shown by ionic solid, this type of defect is shown by the ionic solid having low coordination number and a large difference in size of cation and anion. For example, silver halide, that is silver chloride, silver bromide, silver iodide, etc. These are shown by the Frankel defect. Next we discuss about the difference between. What is the difference? Very, very important to mark question. What is the difference between the Schottky defect and the Frankel defect? Next we discuss the difference between Next we discuss difference between Schottky defect and Frankel defect. Very, very important one. Make a table one side. Schottky defect one side, Frankel defect. That means while going through the distinction, the most important point, first point is always the definition. Mark that. Point 1. It arises due to the missing of a pair of cation and anion in the interstitial site. Point 1. It arises due to the missing of cation from the lattice site and is present in the interstitial space. Interstitial site. Point 2. It decreases the density of the crystal. Point 2. It does not affect the density of the crystal. Point 3. This defect is shown by ionic compound having high coordination number and small difference in size of cation and anion. This defect is shown by ionic solid having low coordination number and there is large difference in size of cation and anion. Mark that. 3 points are there. Point 1 is the definition. Point 2, it decreases the density of the crystal. Here the density does not affect. Here this type of defect shown by ionic crystal having high coordination number and there is a very small difference in size of the cation anion. While in this case that is shown by the ionic crystal having low coordination number and large difference in size of the cation anion. Example: sodium chloride, potassium bromide. Here silver halide, that is silver chloride, silver bromide, silver iodide. It is all about the difference between Schottky defect and Frankel defect, or under the heading of stoichiometric defect. Next, switch over to second part, that is non-stoichiometric defect. Next, move to the second point, that is under the heading of point defect, that is known as non-stoichiometric defect. That means in case of stoichiometric defect, it does not disturb the molecular arrangement. That means radius of the cation and anion remains same. The number of cation to number of anion remains same. But here, that is the opposite is there. It disturbs the regular arrangement. The number of cation and anion is differ. Then this is known as non-stoichiometric defect. Mark that. Again, I draw this one. It is of two types. That is buying. It is carried out by cationic vacancy, and another one is by anionic vacancy. And this cationic vacancy is carried out in two different ways. That is due to the presence of extra cation in the interstitial site, and due to another one is anionic vacancy. That means non-stoichiometric defect is of two types. That is of two types. That is by metal excess defect, and another one is by metal deficiency defect. This metal excess defect is carried out by two different ways. One is known as by the addition of by presence of extra cation in the interstitial site, and another one is by anionic vacancy. And next, another one is metal deficiency defect. Mark that this non-stoichiometric defect is due to, again I repeat, by presence of metal excess defect and by the metal deficiency defect. Come that how this defect arises, move to the point one, that is by the presence of extra cation in the interstitial site. Mark the diagram. Mark that by the presence of extra cation, that is A plus, B minus, A plus, B minus, B minus, A plus, B minus, A plus, A plus, B minus, A plus, B minus, B minus, A plus, B minus, A plus. Mark that extra cation is occupying in the interstitial site. Extra cation occupying the interstitial site in this defect. In order to maintain the electrical neutrality, nearby vicinity an electron is captured in nearby its interstitial site. Mark that this defect, that means the presence of extra cation in the interstitial site. In this type of defect, an extra cation is present in the interstitial site, and in order to maintain the electrical neutrality, an extra electron also entrapped or captured near the vicinity of its interstitial site. As a result, electrical neutrality is maintained. While move to the second case, that is anion vacancy. Mark that. This type of defect is observed. Mark that. One anion is vacant is there. Anion vacancy. An anion is vacant is there. So, in order to maintain the electrical neutrality, an electron is captured. Mark this one. This is the case that when non-stoichiometric defect by metal excess defect is carried out in two way. One is the presence of extra cation in the interstitial site, and one is known as anion vacancy. One anion vacancy is there in this crystal lattice, while to maintain the electrical neutrality, an electron is captured in that position, making a hole, and that hole is covered by an electron. So that electron, where the electron is captured, this is known as F center. F center. F center means color producing. Suitable examples are there. Mark that. Suitable example is there. For example, when sodium chloride crystal is heated with sodium vapor, it produces yellow color. Point 1. Point 2. When lithium chloride crystal is heated with lithium vapor, it produces pink color. Third example, when potassium chloride crystal is heated with potassium vapor, it produces violet color due to F center. Mark that this electron plays an important role for producing color, that is known as F center. For example, when sodium chloride crystal heated with sodium vapor, it produces golden yellow color, similarly due to the presence of F center electron. Similarly, when lithium chloride crystal heated with lithium vapor, it produces the pink color, while potassium chloride crystal heated with potassium vapor, it produces violet color due to the presence of F center. It is all about the deficiency. Non-stoichiometric defect is again two types. One is known as metal excess defect and one is known as metal deficiency defect. Metal excess defect is due to again two types. That is, one is presence of extra cation in the interstitial site and next one is anionic deficiency. Next move to bit 1 is over, that is metal excess defect. Next bit 2 is metal deficiency defect. Next point, that is metal deficiency defect. That means in this type of defect arises when one metal cation is vacant from its lattice site and another one nearby one metal ion increases its oxidation state. Generally, this type of defect shown by transition metal. Mark the diagram. A plus, B minus, A plus, B minus, that is B minus, A plus is missing, B minus, A plus, this is A plus, B minus, A2 plus, B minus, B minus, A plus, B minus, A plus. Mark the defect. Here one cation, that means metal deficiency defect. When metal cation is vacant from its lattice site, while nearby metal ion increases its oxidation number in order to maintain the electrical neutrality. And generally, this type of defect is shown by transition metal atom. Next, last one, that means the impurity defect. Last one is impurity defect. What do you mean by impurity defect? This type of defect arises due to the presence of impurity. In case of ionic crystal, when impurity is added, foreign substance means outside from another one substance which is behave as a impurity is to be added in host atom. For example, in a sodium chloride crystal, when strontium chloride crystal into the sodium chloride crystal, when strontium chloride is added, then one strontium ion replaces two sodium ion, leaving behind one sodium ion vacant. Mark the diagram. Mark that the sodium chloride crystal, Na plus Cl minus, Na plus Cl minus, Cl minus, Sr2 plus, Cl minus, Na plus, Cl minus, Na plus vacant, Cl minus, Na plus, Cl minus, Na plus. Mark that. This type of defect, that is impurity defect, that means one foreign impurity is added to the host atom. Here, to the sodium chloride crystal, strontium chloride is added, as a result of which, as it is 2 plus, so one strontium atom displaces two sodium ion, one occupied by strontium ion, while another one remain vacant. So this type of defect is known as the impurity defect. It is all about little idea about the defect or point defect. Next, switch over to the electrical properties of a solid. Next we discuss electrical property of solid. Depending upon the electrical conductivity, solid are classified into three types. One is conductor, one is semiconductor, and one is insulator. Mark that. Point one is conductor, point two is insulator, point three is semiconductor. Mark that. I repeat again. Depending upon the electrical conductivity, that is, the solid classified into three types. One is conductor, one is insulator, one is semiconductor. Come to the point one, conductor. The solid is said to be conductor if its conductivity varies, that means from 10 to the power 4 to 10 to the power 7 ohm inverse, meter inverse. If conductivity range lies between 10 to the 4 to 10 to the power 7 ohm inverse, meter inverse, then that type of solid comes under conductor. Metals are suitable examples of conductor. Again, conductor are of two types. One is known as conductor are of two types. One is known as metallic conductor and one is known as electrolytic conductor. In metallic conductor, conducting unit is known as the mobile electron, free electron, while in case of electrolytic conductor, the conducting unit is known as the cation and anion. The most important thing is that in case of a metal conductor, on increasing temperature, conductivity decreases, while in case of electrolytic conductor, on increasing temperature, conductivity increases. Come to the second one, that means insulator. The solid is said to be insulator if it has very low or no conductivity. That means conductivity varies from 10 to the power minus 20 to 10 to the power minus 10 ohm inverse, meter inverse. The solid whose conductivity lies between 10 to the power minus 20 to 10 to the power minus 10 ohm inverse, meter inverse, these are comes under insulator. That is non-metals, plastic, glass, rubber, oxygen, nitrogen, sulfur, these are comes under insulator. Move to the third one, that is semiconductor. That means the solid whose conductivity lies between conductor and insulator. That means whose conductivity range lies between 10 to the power minus 6 to 10 to the power 4 ohm inverse, meter inverse, then these are comes under the semiconductor. So depending upon the conductivity range, conductivity ability, solids are classified into conductor, insulator and semiconductor. Next is about to the last heading, that is known as magnetic properties of solid. Next we discuss magnetic properties of solid. Magnetic properties of solid. Depending upon the magnetic behavior, magnetic character, solids are classified into 5 different types. One is a diamagnetic substance, paramagnetic substance, ferromagnetic substance, antiferromagnetic substance, and ferrimagnetic substance. Mark that. Depending upon magnetic behavior, one is diamagnetic substance, one is paramagnetic substance, one is ferromagnetic substance, one is antiferromagnetic substance, and last one is ferrimagnetic substance. Come to the first point, that means diamagnetic substance. These are the solid which are not attracted by the magnet, somewhat repelled by the magnet, and it is due to the presence of all paired electron. If we go through the electronic configuration, electronic arrangement, then all electrons are paired off. Mark that. For example, sodium chloride, water, benzene. In these cases, all electrons are paired up. Non-paired electrons are there. That's why they are not attracted by the magnet, somewhat a little bit repelled by the magnet. These solids are known as diamagnetic solid or diamagnetic substance. Move to the second one, that is paramagnetic substance. These are the substances, that is atom or ion, having the presence of unpaired electron, and they are attracted by the magnetic field. However, when magnetic field is removed, they loses their magnetic character. Some ions is there. That means, for example, CO2 plus, Fe2 plus, Fe3 plus, Cr3 plus, etc. That means some ion is there, possess unpaired electron, they are attracted towards a magnet. But if a magnetic field removed, they lose their magnetic character. Next to ferromagnetic substance. They are strongly attracted towards a magnet. For example, iron, cobalt, nickel, etc. They are strongly attracted towards a magnet. They are permanently magnetized. No doubt, if a magnetic field also removed, they do not lose their magnetic character. It has been observed that in case of solid, the metal ion group together and remain in a small region form a domain. Each domain behaves as a teeny magnet. Mark that. I repeat again. The ferromagnetic substances are strongly attracted towards a magnet. They behave as a strong magnet, even removal of a magnetic force. And it has been observed that in solid, the metal ion group together to a small region, they form domain. Each domain behaves as a teeny magnet. That means when electric field is not applied, then this domain arrange haphazardly to each other, among each other. But when magnetic field is arranged, then the domain are aligned in one direction, in the direction of magnetic field. Mark that. This is the alignment of the domain. Orderly alignment is there. That's why they are behave as a strong magnet. Even magnetic field is removed. This is known as ferromagnetic substances. That is metal like iron, cobalt, nickel exhibit this type of property. So point 1 diamagnetic, point 2 paramagnetic, point 3 ferromagnetic. Next point 4, that means ferrimagnetic substance. These are some substances are there. On the basis upon their domain, they behave as strong magnet. But actually, their dipole moment is zero. Their magnetic moment is zero. Because the domain are opposite to each other. The alignment of domain is opposite to each other. So they behave as diamagnetic. Mark the arrangement of the domain. One is cancelled to another one. So on the basing upon their domain, they expected to have greater magnetic moment, greater magnetic character, but due to the equal and opposite arrangement, their magnetic moment cancel out each other, as a result of which they behave as a diamagnetic substance. For example, MnO, MnO2, Mn2O3, etc. These are shown this type of behavior, magnetic character. Last one, that means diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, and last one is diamagnetic, point 1, paramagnetic, point 2, ferromagnetic, point 3, antiferromagnetic. This one is known as antiferromagnetic. And while the last one is ferrimagnetic substance. Last one is ferrimagnetic substance. That means, similarly, on the basing upon their domain, they expected to have a high value of a magnetic moment. But due to their actual arrangement, they have low magnetic moment and their magnetic character slightly decreases. Mark the arrangement of a domain. Mark that. 2 domain align up, 1 is down, 2 domain align up, and 1 is down. So due to this type of arrangement, previously they expected to a high magnetic moment, but actually their magnetic character is low. For example, Fe2O3, for example, Fe3O4 exhibit this type of magnetic behavior. So, I repeat again, on the basing upon their magnetic character, substances are of 5 types: diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and last one is ferrimagnetic substances. It is all about the magnetic character of solid.